Welcome to Persistent Kernels, a powerful dynamic work distribution pattern that revolutionizes GPU computing. Here we have 4 streaming multiprocessors, the fundamental execution units of a GPU. Each SM can independently process work. Let's examine the persistent kernel code structure. This is where the magic happens. Notice the infinite while loop. Unlike traditional kernels that process one task and exit, persistent kernels stay alive, continuously requesting new work. Each thread uses an atomic add operation to fetch its next task index from the global counter. This ensures thread-safe work distribution. The exit condition checks if we've exceeded the total number of tasks. When true, the thread terminates gracefully. This is where the actual heavy computation happens, processing the fetched data element. Now let's see how we launch this kernel from the host code. The key insight: we launch exactly one thread block per SM. This ensures optimal occupancy and keeps all hardware busy. Watch as the kernel code transforms into resident kernels that will live on each SM. Each SM now has its own copy of the kernel, ready to continuously fetch and process work. All SMs are in the ready state. Let's set up our global memory environment. We have a global atomic counter initialized to 0 and our work items array containing 10 tasks. Now let's watch the dynamic work distribution in action. SM0 requests work by performing an atomic add on the global counter. This ensures thread-safe access. The counter increments, returning the current value as the task index. Each SM gets a unique task. The SM fetches its assigned data from global memory. Notice the green packet traveling from the array to the processor. Now the SM enters compute phase, processing its data. Meanwhile, other SMs continue fetching new work. Excellent. All work items have been successfully processed. Notice how the atomic counter reached 10. Let's visualize this execution on a timeline to see how work was distributed across our 4 SMs. Watch carefully how each SM picks up work as soon as it becomes available. There's no predetermined assignment. It's completely dynamic. Here's the complete execution timeline with time markers. Notice how work is efficiently distributed with minimal idle time across all SMs. When should you use persistent kernels? Let's explore 4 key scenarios where this pattern excels. First, dynamic workloads. When your tasks have vastly different execution times, persistent kernels prevent streaming multiprocessors from sitting idle while others finish lengthy computations. Second, producer-consumer patterns. When GPU threads themselves generate new work dynamically, persistent kernels can immediately consume it without kernel relaunch overhead. Third, graph traversal algorithms. Irregular data structures like breadth-first search or depth-first search benefit enormously, as the frontier changes unpredictably during execution. Finally, megakernels. Complex rendering pipelines like ray tracing with diverse material shaders can dynamically distribute different types of work without leaving the GPU. Persistent kernels transform how we think about GPU work distribution, from static predetermined assignments to dynamic self-scheduling execution that maximizes hardware utilization.